Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 13 for Chapter 4. Chapter 4 is the design with standard modules. The course title is Digital Logic Design or Digital Systems or Digital Electronics. Lecture number 13, we're going to talk about decoders as a standard module. Next slide is a disclaimer for you to read. There are many references in digital logic design. I cite 3 references here. You can find many other references in store at your public library or even internet. Chapter 4 contents. Today we'll talk about decoders and decoder expansion. And we'll talk also about design with decoders, code converters, encoders, multiplexers, multiplexer expansion, design with multiplexers, demultiplexers, read-only memory, RAM, design with read-only memories, programmable logic array or PLAs, programmable array logic or PALs, and complex programmable logic devices, field programmable gate array or FPGA, and also talk about VHDL Design 3 at the end of the chapter. What's the standard module? Standard modules are integrated circuits produced in LSI, MSI, and VLSI packages. LSI stands for low scale integration. MSI, it's medium scale integration, and VLSI, very large scale integration. They are defined depends on how many transistors or gates you have on silicon, every chip. Standard modules include decoders, encoders, multiplexers, demultiplexers, RAM, PLA, PAL, complex programmable logic devices or CPLD, and FPGAs. Now, those devices are integrated circuits. They vary in size and number of pins and even in a price. They could be few cents to few thousands of dollars. So there are many variety of those programmable devices, and they are made by almost every solid-state integrated circuits manufacturers all over the world. And they are very popular nowadays in implementing switching functions, switching systems, even complete computer, you can put it on a device. They have several advantages over discrete components. Standard combinational modules are relatively inexpensive, more reliable, easily available. They are smaller in size, they consume less energy if you replace them with gates, and hence complex digital systems are implemented as modular networks, whereas the functionality of the systems is partitioned to sub-functions, each of which mapped into standard components. Then all components are integrated as a modular network or a modular device, as a complete modular device. So this is, you will save a lot of money, a lot of energy, time consumed in the design, power consumption, weight, and so on and so forth. So are very reliable to design with standard modules. The first standard module that we'll talk about is decoder. Decoders are an input binary decoder. An input binary decoder is a combinational module and inputs and at maximum 2 to the power n outputs. So if n is 2, the outputs will be 2 to the power 2, 4. If n is 3, the outputs will be 2 to the power 3, which is 8. If n is 4, 2 to the power 4 will be 16, and so on and so forth. So the characteristic of the decoder is that for every combination of input values, only one input is active at the same time. So at a time, only one output will be active, and the output to be active, either active high, which is logic 1, active low, which is logic 0. Hence, effectively, the decoder is a min-term generator when the outputs are active high, with each output corresponding to exactly one min-term, and the max-term generator when its outputs are active low, with each output corresponding to exactly one max term. The decoder may have one more input enable lines, which they may be active low or active high. Now, always the indication for a signal to be active low, if the output is active low, we will put a small circle here at the output to indicate that it is active low. The same thing with the enable. If the enable is active low, we put a small circle here to indicate that the enable signal is active low. So we have inputs from x0 as the least significant bit to xn minus 1 as the most significant bits, and the output from y0, y1 up to y2 to the power n minus 1. So for instance, if we're having two inputs, x0 and x1, you will have four outputs, which is y0, y1, y2, and y3, because 2 to the 2 is equal to 4. And y3, because 2 to the 4 minus 1, so this is y3. The subscript here will be y. So this is a very good representation for an encoder that's a min-term generator with one enable line and 2 to the power n outputs and n inputs. Again, the decoder, if the outputs are active high, it will be considered as a min-term generator. If the outputs are active low, it will be considered as inverted min-terms or max terms. As you know, the small m prime is equal to capital M. It means that the complement of a min-term is equal to max term and vice versa. Let's try to design a decoder. A decoder, you can buy it as an integrated circuit. But also, we'll try to understand how to design it. And by understanding how to design a decoder, we'll be able to use it and utilize it in building combinational networks and systems. So we'd like to design a 2 to 4 decoder active high output, it means min-term generator. So here I will have two inputs at the truth table A and B, and I have four outputs, y0, y1, y2, y3. Since they are active high, if I have 0, 0, y0 will become 1, and all the other outputs will be 0 because we will have one active at a time. If I have 0, 1, so I will have, this is min-term 1, I will have y1 is active, which is 1, and all the others will be zeros. If it is 1, 0, which is min-term 2, I will have y2 is equals to 1, all the others will be zeros. If 1, 1, I will have y3 is active, which is 1, and y0, y1, y2 will be zeros. So the logical equations for y0 is m0, min-term 0, which is a prime, b prime, and y1, which is m1, which is a prime, b, y2 is m2, term 2, which is ab prime, and y3 is m3, which is ab. Now, from these logical equations that we really got them immediately from the truth table, you don't need K-map because you have 1, and the prime implicant, the only term could be represented with 1 is a prime, b prime. y1 is all zeros except here 1, which is a prime, b. y2 is 1 here, which is a, b. And y3 will happen to be 1 only when a is 1 and b is 1, a, b. This is min-term 3. So this is a representation of y0, y1, y2, y3. And the logical equations could be translated to hardware, as you can see. So we have two inverters to invert A and B. A is the most significant bit, and B is the least significant. So we have two inverters. Now, to generate Y0, I need A prime, B prime, both of them inverted, as you can see. To generate Y1, I need A prime, which we took it from here, B, uninverted. Y2 would be M2, which is A, B prime, so take A. This is B prime taken from here, and A is taken from A. See, it's connected to A before version. So this is AB, and Y3 will be AB. AB before the inverters, A and B is taken to Y3, and this is basically will give me the hardware implementation. I needed two inverters and 4 AND gates to implement a 2 to 4 decoders with active high outputs. Now the second one, I'd like to add, modify this by adding an enable signal. If we add an enable signal, I'd like to design 2 to 4 active high outputs. It means minterm generator and active high enable input. So with the enable signal must be 1 all the time for the decoder to function, to have an output, to have a valid output. If the enable is 0, regardless of the inputs A and B, the outputs, all of them will be inactive zeros, will be inactive zeros. So you get 0, 0, 0, 0, none of them is active. Okay? Now again, if enable is 1, and if I have 0, 0, Y0, 1, 0, 1, I will have Y1 is 1, and 1, 0, I will have Y2 is 1, I will have Y3 is 1. Conditionally, that E has to be active, 1, 1, 1. Once it is 0, all the outputs will be 0, regardless well the values of A and B are. So we say don't care, it does not care what values we use. So here, how we express Y0? Y0, if we read it again, will be from the truth table. E is 1, A prime, B prime. Y0 is 1. Y1 is 1, E, A prime, B. Y2 is E, AB, and Y3 is E, AB. And those are the logical equations for Y0, Y1, Y2, Y3. We get them from the truth table. We don't need gamma because it's so simple. And we have the hardware, the logical gate level implementation. For the decoder in design 2, we have it here. We have A is the most significant bit, B is the least significant bit, with two inverters, and we added E. So as you can see, we have E, A prime, B prime. A, it's the signal fed them to every AND gate. So we have A prime and B prime, and E, A and B to get Y3, and so on for Y1, 2. So direct implementation, we get the hardware circuit for the decoder in design 2, which is 2 to 4 decoder with active high outputs and active high input. So this is, again, it's the minterm generator. We added an enable signal. The next slide will design a 2 to 4 decoder with active low outputs. It means it's now a maxterm generator, okay, and without an enable signal. So AB, when AB is 0, 0, I will have Y0 will be active low, which is 0. Y1, Y2, and Y3 will be 1. So what we will have Y0 is 0, 1, 1, 1. Why it is active only at 0, 0. It is inactive at the input 0, 1, 1, 0, or the same thing with Y1. It's active only when the inputs are 0. So we'll get active at 0. Y2 will be active 0 and the output when the inputs A and B prime. A and okay, it will be 0. Say A prime B, A prime or B is a max term. And it will be 0 for y3 when A is equals to 1 and B is equals to 1, A prime or B. So from the truth table, we can generate the logical equations for y0, y1, 2, y3. If you wish, you can draw K-maps if you have a problem with this. But without actually K-map, what we can say it's y0, it's m0 because we are the zeros, and it is A or B, or it is A prime, B prime, because the complement of a min term is a max term. So m0, this is m0 prime, small m0 prime. So the max term is 0, it is A or B. The same thing with y1. y1 be A or B prime. We can read 0, it's A prime B. And y3 will be A prime or B prime. Or you can find it as the complement of AB prime. Get 0, so you can count this A prime, B. Once we have those equations, okay, we can implement them easily by using NAND gates, because as you can see, it is complemented in terms, so therefore we use NAND gate, and we end up with this hardware circuit. 2 to 4 active outputs is it is a max term generator. Okay, very easy, beautiful. Let's look at this design modified with an enable, with active low enable. So I added an enable input. So I will get, when I have enable input 0, we will have an active output one at a time. If the enable is 1, regardless of the inputs, all the outputs will be disabled, which is they are active, which they are ones, because it is active low. So if they are ones, it means I don't have any output active. All the outputs are inactive. But if they enable zeros, okay, so how we read y0? y0 will be 0, 1, 1, 1. So 0, when you get y0 will be the max term, 0, which is E, A, or B. Or it is E prime, A prime, B prime, all prime, which is the complement of the min term, is max term. The same thing, y1, it is 0 when I have E or A or B. It is 0 when I have E or A prime B. And y3 is 0 when I have E or A prime B. So you get the logical equations. And again, it is the same previous circuit in design 3, just we added an enable signal. I have to input the enable signal, okay, and take it to an AND gate to implement this part of the logical equation. So we are using NAND gate, we are not using OR gate. If we are using OR gate, I don't have to invert E. OR gates, we are not using NAND gates, so we are implementing Y0, Y1, Y2, Y3 NAND gates, and 3 inverters, one for the E, and one for the A, and one for the B. And this is the decoder in design 4. Now, we will talk about decoder expansion. When larger sizes of decoders are needed, they can be formed by interconnecting 2 or more small packages or chips of decoder and some additional discrete gates. And there are 2 approaches to expand the decoder size. Coincident, or 2-dimensional decoding scheme, or 3 one-dimensional decoding. Now, in the coincident or 2-dimensional, we will have 2 decoders. One is n to 2 to the power n, and the other is m to 2 to the n, horizontal and vertical. Plus gate switching matrix can be interconnected to form n plus m to the power m plus n. So, if we need to, in this example, to generate a decoder which is 4 to the power 4 to 16 decoder. So 4 to 16 decoder will have AB and CD. We'll take AB to horizontal decoder, horizontal lines, okay, and CD we take them to the vertical decoder, which generate all the lines. And those two, the intersection of those two, we take them to an AND gate, to AND matrix to generate all outputs, which they are active high or could be active low. Change the matrix to NAND gates and they are active. So in this case, we are looking at active high expansion. So for instance, if we have the input 0, 0, the output 0 will be active. If I have 0, 0, this 0 only will be active. Only active, this 0. And 0 and 0, you'll get Y0. Y0. So if this is active high and this is active high, the AND gate Y0 will be active, while all the other outputs be inactive, zeros. Again, if I have 0, 0, this line will be active, this horizontal line, this vertical line, which is the output of 0, 0, this is 0, 0, so this will be active, so I will have Y0 will be active, Y0 will be active only, because all the others will be inactive, because the inputs for Y0 is the output from first decoder, which is the 0 with 0. If you look at the input for this, it is 1 with 0, which corresponds to Y4. Okay, and so on and so forth. So we'll have 1 inactive time, and by doing this, by using coincident decoding, let's take another example. We have 1, 3 will be active. So 3 is taken to Y15, Y14, Y13, and 12. And if I have 1, 1, 3 will be active, which is taken to Y15. So Y15 will have 2 inputs active, the output Y15 will be 1. All other outputs, all other Y's be zeros. Okay? So clearly the coincident decoding will work very successfully with a gate matrix, as you can see. And we use less than number of decoders with the gate matrix to add to the design to have a successful expansion. So this is, we refer to it as coincident or two-dimensional decoding. Let's look at what we call a tree decoding. In a tree decoding, we decompose the decoder to number of levels. The node, the tree, is a decoder representing the first level of the tree. The inputs to the node decoder are the most significant bits of the input set, and the outputs of the decoder are the enabled lines to the next level. The outputs of level 1, if we have second level, either enable signals for level 2, and so on and so forth, in a tree, okay, and until we get the last output. So we need actually, in 3D decoding, we have different designs based on the position format, so we have to decompose based on the availability of chip. Let's take an example. We need to design a 5 to 32 line decoder. So we need 32 outputs, and we have how many inputs? We have 5 inputs. So we have 5 inputs set. So we can use the 32 could be divided 4 by 8. We have 4 the output of level 1 by 8, which is the output of each decoder in level 2. Or they could be 8 times 4. If we have a 3 to 8 decoder in the node, then we have so we can use 8 by 4 or 2 by 16. So 8 by 4 or 2 by 16. So we have any scheme that we can use. What we are using here, we are using 4 by 8. 4 by 8, we can choose the decomposition based on the availability of the chip. Okay, so hence actually we can have 4 2 to 3 decoders as shown here as the second level of 3, or 8 2 to 4 decoders, or 4 to 16 decoders as we wish. Because 16, so we can have 2 4 to 16, because 16 times 2. So actually the expansion will be based on simple algebraic formula. Here we have 4. So the 4, we can enable 4 decoders, and 4 times 8, because we have those 8 outputs. Since we have 4, so we have 8 outputs, okay, will give me 32. If I use 2 16 decoders at the level 2, also I will get 32. Okay, and the 2 16 decoders enabled by simply we can enable them by simple gates if we want to. Okay, because the 16 decoders could be enabled by only the most significant bit A. Okay, so we can have the outputs 2 by 16, 2 4 to 16. Okay. If we need the output to be 4, for instance here, if we use 2 to 4 decoder on level 2, how many decoders do we need? We need 8, because 8 times 4 will be 32. So we look at the output. We start with the most significant bit at the node decoder. So we have A and B. So if A and B are 0, 0, the 0 line will be active, which will enable the 3 to 8 decoder. So if I have 0, 0, 0, Y0 will be active, and all the others will be disabled. If A and B are 1, 1, so this line will be active. So this decoder will be active. The last one, the one at the bottom, will be active. And if I have 1, 1, 1, Y31 will be active. And all the others will be 0. All of those will not be selected. So 3 decoding is beautiful. We will look how many output lines, and we can design accordingly based on the availability of chips. So this is a decoder expansion with 3 decoding, and by doing that, actually we can have a larger decoder to implement our functions if a larger chip is not available at that time of the implementation. Okay, this will be the end of this lecture 13 of chapter 4, and I would like to thank you so much. So please subscribe, and hopefully to see you very soon. Sincerely, Dr.